This is the final 6.3 video. We're going to look at calculating and interpreting probabilities involving geometric random variables. So a geometric setting arises when we perform independent trials of the same chance process and record the number of trials it takes to get one success. On each trial, the probability of a success, P, must be the same. So a geometric setting is similar to a binomial setting, except for the fact that there's no set number of trials. So if you remember, binomial settings are checked by checking your bins. So the outcomes are binary, a success or a failure. Trials are independent. For binomial settings, there's a set number of trials. For geometric, there's no set number of trials, and the probability of success is the same. So really, it's the same thing as binomial, except there's no set number of trials. So geometric settings, you're not counting the number of successes in a set number of trials. You're counting how many trials it takes to get the first success. I'm going to explain this formula here after we do an example problem because it'll make more sense. So let's look at a similar scenario that we've talked about. A local fast food restaurant is running a draw 3, get it free lunch promotion. After each customer orders, a touchscreen display shows the message, press here to win a free lunch. A computer program then simulates one card being drawn from a standard deck. If the chosen card is a 3, the customer's order is free. Otherwise, the customer must pay the bill. So let X equal the number of customers it takes to get the first free order on a given day. You might remember we've done this problem before in a binomial setting where instead of counting the number of customers it takes to get the first free order, we said something along the lines of, what's the probability that 3 customers win in 50 customers? So there's a set number of trials. Here, we're going until we get the first success. So what's the probability that X equals 3? What's the probability that the first success, the first free lunch comes on the 3rd customer? So you got to think about what that means. If the first person to win is the 3rd customer, that means the 1st and 2nd customer did not win. So you got to figure out what the probability of success here is. And in this problem, since they're looking for a winner is a 3 from a deck of cards. There's 52 total cards in a deck, and there are 4 3s in the deck of cards. So there is a 4 out of 52 chance of winning a free lunch, which means there is a 48 out of 52 chance of losing. So there was 2 losers and 1 winner. So you can see I wrote the probability of X being 3 means the first person, it was a failure, did not win, a failure did not win, and the 3rd one was the first success. So you have to find the probability of someone not getting a free lunch and not getting a free lunch and getting a free lunch. So we're multiplying these together, and the probability is 0.0655. So now this should add some clarity to this formula up here. This is the probability of Y, the geometric random variable, they call it Y instead of X, is equal to K number of successes, or K number of trials for the first success. So 1 minus P is the probability of a failure, to K minus 1 is the number of failures based on the number of successes. So in our case, K was 3. So this first probability of a failure was 3 minus 1. There were 2 failures. And then it always ends with 1 success because the geometric random variable goes until you have your first success. So we could have rewritten this as 48 52 squared times 452. We would have got the same thing. But I want to show you how to do this in the calculator as well. It's called geometric PDF, and it's similar to how we did binomial PDF. In the calculator, we're going to go to second distributions. And instead of binomial, if you go down, you'll see PDF, Geomet, PDF, and CDF. So PDF is exactly equal to. CDF will give you the value that is less than or equal to. So we asked for the probability of X being exactly equal to 3. So P is the probability of success. So there is a 4 out of 52 probability of getting a 3. And notice I put it in as a fraction because it's a repeating decimal. So I don't want to round and put in my probability. I want it to be exact. And then X is the number of trials it takes to get the first success, which we said was 3. So paste it, you can see geometric PDF. P is your first input and X is your next input, and it will give us 0.0655, just like we saw before. So this is your formula for the geometric PDF in the calculator, probability of a success and the number of trials to the first success. So I'll write out the probability of X being equal to 3 like we saw in the calculator. And interpreting this probability, we would say the probability that the first customer to win a free lunch is the third customer is 0.0655. The next problem says, what's the probability that the first customer to win a free lunch is the first or second, because it's less than 3, so it's not including 3. So this could mean it's the probability of X being 1 or X being 2. So if X is less than 3, that means it's equal to 1 or equal to 2. So we're going to add the probability of being 1 and 2. If it's 1, that means there were no failure. It happened on the first trial, so there were no failures beforehand. So the first card was a 3. If it was the second, then there was a failure, and the second one was the first success. So add those together and you get 0.1479. The easier way to do this, though, is to use geometric CDF in your calculator, because CDF gives you the value that is less than or equal to some number. So first we have to rewrite this. Since my calculator says less than or equal to, I'm going to write it as a less than or equal to statement. And so if it's less than 3, then it's going to be less than or equal to 2. Both means the same thing. So that means my input is geometric CDF, probability of success is 450 seconds, and X, the number of trials it takes for the first success, is 2, and we'll get the same exact value. I'll show you in the calculator, and then we'll do the next problem. We'll go to second vars to get to our distributions, find geomet CDF. Our probability of success is still 4 out of 52. We said the number of trials X is 2. And you can see we get the same value that we calculated by hand. The last geometric probability says find the probability of X being greater than 5. The issue with this one is our calculator will only tell us less than or equal to some value, so we need to rewrite this as a less than or equal to statement. And since it's asking for greater than, we're going to have to use the complement rule to write this down. To help figure out how to write this using the complement rule, sometimes it helps just to write out a start of the outcomes, because geometric random variables, first off, can never be 0, because there has to be at least one trial to get a success. And they could go for a long time. So I've written out that it could be from 1 to 10, or it keeps going. So the probability of X being greater than 5 would be 6, 7, 8, 9, 10, and so on and so forth. So I've highlighted this probability here. This is what I'm trying to figure out, which means the complement would be 5 or less. So that's going to help me to write out the probability of X being greater than 5 using the complement rule with a statement that says less than or equal to. Now I can see the probability of X being greater than 5 is the same as 1 minus the probability of X being less than or equal to 5, because the complement rule is saying that it's either going to be this or this. One of these will occur. And so now I can use my calculator to solve with this statement, because I have to have it written as less than or equal to some number. So I'll throw this statement into the calculator and see what our final answer is. I'll start with 1 minus, then go to my distributions. I want it to be 5 is X. And let's just make sure it remembered the 1 minus. There we go, 1 minus, and then it's going to calculate 0.670. The probability it takes more than 5 is 0.06702. So think about what we just did here. We had to calculate the probability of x being greater than 5. So these are the values that are greater than 5. So I found this probability in the calculator and subtracted it from 1 because that left me with this value here. That's the way the complement rule works. Finally, let's calculate the mean and standard deviation of a geometric random variable. And this is pretty simple. The mean of a geometric random variable is 1 divided by p, and its standard deviation is the square root of 1 minus p divided by p. Notice the square root is only in the numerator here. One thing to make a note about with geometric random variables is they are always skewed right. Binomial random variables can be many different shapes and sizes based on the number of successes or number of trials and the probability of success. But geometric is always going to be skewed right. Here's the geometric distribution for the problem that we just did beforehand. Because you can see the probability of it taking one more trial, it continually gets smaller and smaller and smaller and smaller. And you can't write out all of the outcomes because it could keep going and going and going. Also notice that it starts at 1 because geometric random variables have to have at least one trial to have the first success. So let's calculate the mean and the standard deviation and interpret those based on the previous problem where they were asking customers to play this game until they got the free lunch. So the probability of success was 4 out of 52. The mean is 1 over p, 1 over 450 seconds, ends up being 13. So if the restaurant runs this lunch promotion on many days, the average number of customers it takes to get the first free order would be about 13 customers. Remember, the mean is always interpreted from a random variable as a long run. And so if they run this promotion many days, the average number of customers it takes to win the free lunch would be about 13 customers. To calculate the standard deviation, we're going to use this formula here, and we'll interpret that as well. Remember to only take the square root of the numerator, and you get 12.49, which means if the restaurant runs this promotion on many days, the average number of customers it takes to get the first free lunch would typically vary by about 12.5 from the mean of 13 customers.